Ready? Okay, so we should get started. Welcome to the second Simons Institute Open lecture of this semester. So as many of you probably know, these lectures are an occasion in which we invite distinguished visitors to the Simons Institute to speak to a broad scientific audience and illuminate some of the ideas that are being discussed in the Institute's programs. So this semester we're running two programs, one on quantum Hamiltonian complexity, which is the subject of today's talk, and the other on evolutionary biology and the theory of computing. Both of these programs are a good illustration of the one of the main goals of the Institute, which is to apply concepts from the theory of computation to other scientific disciplines and explore connections with them. Disciplines such as, Disciplines such as physics, chemistry, economics, biology, and so on. So in particular, in the quantum Hamiltonian complexity program, we have computer scientists and condensed matter physicists rubbing shoulders and trying to understand some fundamental properties of quantum systems. So with that in mind, let me introduce today's speaker, Dorit Aharonov from the Hebrew University in Jerusalem. So Dorit has been a professor of computer science in Jerusalem since 2001, and she also did a PhD there. In the intervening years, she spent time as a postdoc and as a visiting scientist in various other places, including Caltech and the Institute for Advanced Study in Princeton, and also, pleased to say, UC Berkeley several times. She comes from a family of distinguished physicists and mathematicians, and she apparently grew up on Einstein Street in Haifa, and therefore it's not that surprising that she chose the career path that she did. So in the meantime, Dorit has become recognized as one of the leaders of the field of quantum computation. We're very pleased that she's been able to spend substantial time at the program this semester. She's one of the organizers of the program and also was a co-organizer last week of a very successful workshop on quantum games and protocols. Her research interests span a very broad range of topics in quantum computing, including quantum fault tolerance, quantum algorithms, quantum cryptography, and the emerging field of quantum Hamiltonian complexity and connections between quantum mechanics and traditional classical computational complexity. And indeed, that's the topic of today's talk. Maybe she'll also explain this picture of the tiger as well. Thanks very much.
So, thanks a lot, Alistair, for this very nice introduction, and it's an honor to be here. And so what I want to talk about today is really to tell you a little bit about what's going on in the quantum Hamiltonian complexity program, and maybe at the end we'll understand also this logo of the program. So if I don't get to it, ask me. So we really, in this program, study quantum mechanics. Now, quantum mechanics is a theory that has been really tested, and there have been hundreds of thousands of experiments probably testing it, and it's highly established. And still, it's very common practice to say that we don't understand quantum mechanics. So there's this famous saying, if you think you understand quantum mechanics, then you don't understand quantum mechanics. And really, I actually don't understand this saying, because also if you don't think, that you also don't understand. And it's usually attributed to Feynman, but I think it's only by default. There's no evidence that Feynman said it. But in any case, it's sort of common practice to say we don't understand quantum mechanics. So let's just review the basic principles of quantum mechanics that we say we don't understand. Okay, so there are two such basic principles I want to focus on. One is the superposition principle, which says the highly counterintuitive thing that a quantum system can be in a superposition, a linear combination of all its possible classical states. So for example, a spin that can point up and down can also be in a linear combination of those states. And likewise, a cat can be both dead and alive at the same time. And we have this beautiful mathematical formalism of assigning to such a quantum system, say it has two states, so we call it a quantum bit or a qubit, a Hilbert space, a vector space of dimension 2. And we have two basis vectors that correspond to those classical states. But in general, a quantum state is this linear combination of these two basis states denoted with these up and down, for example. So in general, we have some vector, a linear combination of those states. Okay, so this is really a counterintuitive basic principle. And then there is the other basic principle, which is the measurement principle, which is also highly counterintuitive. It says the following. Suppose I want to measure the system in this funny state, superposition state, then the outcome is, if I measure it in the basis up and down, the outcome will be either up or down probabilistically. So the quantum mechanics says that there is absolutely no way to predict the outcome of the system, even if you know exactly the quantum state. So the outcome will be probabilistic, and as you probably know, the probabilities depend on the coefficients in front of the up or down, but the point is that you cannot really predict what's going on. And these two principles are really highly counterintuitive. So they are so counterintuitive that it's hard to swallow, and many people try to find ways to bypass those principles. And so, is it possible to maybe move like this, to have someone sort of shift this so that? Okay, so Einstein, Podolsky, Rosen famously found this Epr paradox, which sort of tries to point at the problem in quantum mechanics, or tries to say that quantum mechanics is incomplete. And basically, what they did is they took. I'm not going to explain the Epr paradox exactly, but they looked at the quantum state, which is very interesting, which is called the Epr pair. And that quantum state is a state of two particles, which are in superposition. So if the first particle points up, the second particle is in the state down, and if this first particle is down, the second particle is up. So they're in superposition of both these configurations. Okay, so what they showed, what they basically pointed at, is that this highly correlated state sort of leads to something which Einstein liked to call a spooky action at a distance. So basically, this Epr state is highly correlated not only in the basis of up and down, but in any basis that you look at it, they're highly correlated. And these correlations seem too strong. And it took 30 years for John Bell to actually find a more mathematically rigorous way to say this thing, and to find inequalities, called Bell inequalities, such that any physical theory that is not so counterintuitive like quantum mechanics would satisfy those inequalities, whereas the Epr pair violates those Bell's inequalities. And lo and behold, Alain Aspect at the early 80s gave experimental evidence for this fact. So gave experimental evidence that quantum mechanics really violates those Bell inequalities, so it does behave counterintuitively. Okay, so these counterintuitive things can also be taken one step further, and to the following scenario. So suppose Alice has a state, and she wants to transmit this state to Bob. But they're separated by some river or something. They're not allowed to send quantum states in any way. So still she can do it if somehow they manage to meet before and share a quantum Epr pair. So if they manage to share this Epr pair, then it can serve as a substrate upon which every other quantum state can be sent if they only communicate classically. Okay, so here this goes like this. And even that teleportation was checked, and there's experimental evidence that, there are teleportation over more than 150 kilometers now, various systems. And okay, so in what sense do we say that we don't understand quantum mechanics? I mean, if we can take all these principles and actually play with them so nicely and predict experimental results and manage to actually perform those experimental results, and everything works nicely, then I would say we do understand quantum mechanics to some level at least. So what I would like to say only for this talk, and don't catch me too strongly, but only for this talk I would like to say that this lack of understanding of quantum mechanics is sort of like a spoiled kid lack of understanding. We can do everything with it, but it's not to our liking because it doesn't behave like what we would like to behave. So we say we don't understand it. But we can make all predictions. So for this talk, I want to tell you about what we really don't understand about quantum mechanics. So what we really don't understand is the high complexity limit of quantum mechanics. Okay, so what happens in quantum mechanics when we add many particles together? When we put not 2 particles together, but n particles together. So by the superposition principle, we just have to look at all the possible configurations of the particles and look at the states which are superpositions of those. So how many configurations do we have for 1, 2, 3, n particles? For 1, we have 2 configurations. For 2, we have 4. Each particle we add multiplies the number of configurations by 2. So eventually, for n particles, we have 2 to the n possible configurations. And this is, so mathematically, there is a nice description by tensor product of n Hilbert spaces describing each the qubit. But if you're not happy with this description, hard to see, you just have to remember this thing. A quantum state of n particles, n quantum bits, in general is a superposition of exponentially many possible configurations. And to describe it, you need to describe the coefficient in front of each one of the 2 to the n possible configurations. So this is really where quantum mechanics, the difference between quantum mechanics and classical mechanics goes to the next level. Why is that? Because classical systems of n particles require only n or 6n numbers to describe. If you're talking about, say, molecules in a gas, you describe momenta and location. 6n parameters are enough. For quantum mechanics, you need 2 to the n parameters. So this is a really humongous size of description compared to this linear growth. We have this exponential growth of a description. And this is what we really don't understand in quantum mechanics. It's this high complexity regime. And what I want to say by that is that we really don't understand it, meaning it's not that we don't like it, but we don't have good descriptions or good predictions for this regime. So if you look at this Hilbert space of exponential size, there's basically just a tiny little fraction of the states that have efficient descriptions. Just by counting arguments, most of the states, even to very crude approximation, cannot even be pointed at, or let alone described, simulated, etc., or manipulated or predicted. So this boils down to those states having much more complicated entanglement structure than even the EPR pair that we didn't understand before. Most of the data that we need to write down basically lies down in the intricate correlations between those particles. And we'll refer to that as multiparticle entanglement. So this sort of points at the difficulty of simulating quantum mechanics, which was noticed already by Feynman and independently by Manin and Benoist in the early 80s. And it sort of points at a very interesting point of view of quantum mechanics, which is its relation to computational complexity. There is an issue of quantum mechanics of many particles, which sort of is problematic from the computational point of view. And so it suggests a new limit to look at in physics. So we're used to looking at different various limits in physics, Planck scale, high energy. So this is a new limit to look at, the high complexity regime, or the high computational complexity regime. Okay, so, okay, now, this high complex regime is not only a disadvantage. Of course, it's also an advantage. This lies at the heart of everything that we know how to do in quantum mechanics, in quantum computation. Those highly entangled states are crucial for quantum algorithmic speedups, for example, for the factoring algorithm of Shor, or other algorithms that you may not have heard of, like graph reachability or approximating various knot invariants. And okay, so these highly entangled quantum states are crucial there, and they're also crucial for all the other phenomena that we encounter in quantum computation. So be it the security of quantum cryptography, or the questions of which quantum systems can we simulate, or the notion of quantum error correcting codes, in which it's very essential that we spread the entanglement over many particles. And it's also crucial in the difficulties of implementing quantum computation. Okay, so understanding highly entangled quantum states is really at the heart of both the things that we can achieve in quantum computation complexity, or in quantum by quantum computers, or by studies of quantum computers, and it's also at the heart of the difficulties that we encounter. And this is really what quantum Hamiltonian complexity is about. It's really the study of quantum states and quantum dynamics of those states from a computational point of view. Okay, so it's basically a marriage of condensed matter physics and computational complexity, where we take some from both. So in condensed matter physics, there's many years of research of specific examples of very interesting quantum states and quantum Hamiltonians, with many heuristics that were derived. And then from computer science come various questions that we have learned to ask about highly complex systems. And now we can ask them about those physical systems. So if we put those together, we sort of take from condensed matter physics the objects, the local Hamiltonians and the ground states, and we ask about them questions that come from theoretical computer science, like, are there efficient descriptions of those states? Efficient meaning polynomial. What about algorithms to map those states to other states? What about simulating quantum systems by other quantum systems or by classical systems? And reductions, mapping those systems to others. And this era, which has been mainly going in that direction in the early days of quantum computation, where we only took the model and then used it for algorithms, this era is now also now has its opposite direction. And basically, it's not just that the edges of the two fields meet, but it's really the core questions in both fields that are tightly related in ways which are really, they're not artificial. They're very deep connections between things that might seem very different on the surface. Okay, so what I want to tell you about today, in the remainder of the talk, is is trying to get at two main ideas in this area, and from which various other ideas branch, and which lie at the heart of the three conferences that we're having in this program. Now, I've listed here three main ideas. So the first one is testing quantum mechanics, which I'll talk about, robustness of quantum systems, which I'll talk about next, and then the last idea, actually I think that Ignacio will talk about in the next open lecture on this program, so I won't talk about that. So, okay, so let's move on to testing quantum mechanics. What do I mean by that? Okay. How to test quantum systems, a computational view on the foundations of quantum mechanics. I'll try to explain this picture at least. And it's based on various works. I might have forgotten some. Okay, so what's the question? Let's look at a physical experiment in the most naive way. How does a physical experiment look? Okay, so we have some physical theory that we want to test. Now, a usual physical experiment looks like this. There's a theorist, there's a theoretician, and there is an experimentalist. And the theoretician takes the theory and makes some prediction. There's an experimentalist who performs the experiment. And then they meet and they compare their results. Okay, and if there's a problem, they throw away the theory, or they say mostly that there was a problem with the experiment, and they try again. Okay, so this is very naive. This is how experiments work. But if you look at it again, you see that actually in quantum mechanics, at least in the high complexity regime of quantum mechanics, this paradigm breaks down. Why is that? So let's look at a computational complexity point of view. Again, from a computational complexity point of view, let's look again at what I've said before, which you were happy with. But let's just phrase it from a different perspective. So, okay. So what we said before is that what we observe is that quantum evolutions, even quantum evolutions that take polynomial time, seem very difficult to simulate by classical evolutions. So if we look at the class of problems which can be solved by classical computer efficiently, this is denoted by BPP, bounded probabilistic polynomial, but you don't have to remember that. This seems to be strictly smaller than the class BQP, which is the same but with quantum computers. Okay, so those problems that I talked about before are here, but we don't know that they're here. Okay, so we think that these things are different. We think that they are. So we widely believe that BQP is strictly larger than BPP. And there's another belief that we add to it, which is that we believe that those BQP evolutions, those BQP algorithms, can in principle be physically implemented. So we believe that there's no physical obstacle to building a quantum computer. Okay, so together, what do these things say? They say that we believe that there are physical evolutions that cannot be simulated efficiently by classical computers. Okay, so let's go back to the picture of the experiment and explain it again. Okay, so here's a physical experiment. We have those two sides. But now let's try to test quantum mechanics at the high complexity regime. So we are placing here the theory by quantum mechanics. And now the problem is this. The experimentalist can continue doing whatever he wants to do and perform the experiment, but the theoretician part of the story cannot be achieved, simply because we cannot simulate. We cannot make a prediction according to the theory because we don't know how to simulate those evolutions. Okay, so this is sort of a very fundamental observation. We cannot really test quantum mechanics at the high complexity regime. So experiments which test quantum mechanics theory are supposed to be compared to the predictions, but we cannot make those predictions. So what do we compare things to? Okay, so So the high complexity limit of quantum mechanics cannot be tested using the usual predict and compare experimental paradigm, which is a disturbing thing because as far as I think most experiments, if not all, lie in this predict and compare paradigm. Okay, so we see here the attempt to so this guy who's trying to tie the tiger is really trying to test or trying to command or to control this highly complex system which he can't really control. Okay, so this question leads to several daughter questions. So first still, is quantum mechanics really falsifiable? In the high complexity regime, at least. Maybe all the experiments that we've done so far only tested quantum mechanics in its low complexity regime. And maybe there exists an alternative quantum mechanical theory, which QM prime, which agrees with quantum mechanics on everything in the low complexity regime, but does not have this exploding computational complexity, exponential explosion. So really the question is, can we experimentally test all physical aspects of quantum mechanics, including its high complexity regime? Okay, second question is more oriented to the experimentalists. If you're an experimentalist and trying to build your quantum computer, how do you actually test that it is doing what you want? If it's claimed to be a quantum computer, how do you know? Okay, and then a cryptographic aspect would be, suppose you distrust the people that you're interacting with, and now you can ask, how can you safely buy a computer from an untrusted company if it's telling you that it's a quantum computer? How can you delegate computations to this untrusted company? How can you provide a grant to an untrusted experimentalist? So, okay. So the alert listener might have already noticed that there is a partial answer to this, right? I mean, Shor's factoring algorithm provides some partial answer because it's a point outside of it's a problem that we believe cannot be solved by a classical computer efficiently, but yet we can test it. Okay, so so it provides a recipe for an experiment that's outside of the usual scientific paradigm. So what's going on here? Okay, it's some kind of a weird experiment because it's not. So what's the difference? The difference is that the theoretician does not have to predict the factors of the number. It has to just predict that the verification process of multiplying the numbers will result in exactly n, the number that we're trying to factorize. So this is a mild difference, but still it puts the experiment outside of this classical of this class of impossible experiments. Okay, so yet it's not a good enough answer. Why is that not a good enough answer? So first of all, factoring is probably not quantum universal. And secondly, what if I want to test a small quantum system, like 100 particles? Even if it factors numbers, it will factor numbers that we can factorize efficiently, and it also cannot really factorize big numbers. So how do I test it? Okay, so really we want to provide some kind of a test for a more general class of quantum evolutions. In fact, for universal quantum evolutions, for any quantum evolution, can we test general quantum evolutions? Okay, and the answer is yes. Using fundamental ideas from computer science, you can test the theory of quantum mechanics, even though we cannot make predictions for it. Okay, so how does this go? So let's look a little bit closer into why did Shor's algorithm for factoring succeed, even though it's not succeed in getting around the usual type of experiment pitfall. Okay, so the reason is that really, so to explain it, maybe we look into something which is very similar to Shor's algorithm, if you look at it correctly, and it's a very profound idea in computer science, and that's called interactive proofs. Okay, so interactive proofs were invented by Goldwasser, Micali, and Rakov long ago in '85, and what are they? So imagine now a completely imaginable entity of an all-powerful prover that is completely unlimited, but is untrusted by the verifier who wants to verify some claim. Okay, now they're allowed to interact between them. And the verifier wants to be convinced and to use the amazing power of the prover, but she doesn't trust him. And it turns out that the power of interactive proofs is much more powerful than what she can do on her own. So the verifier can be convinced of things much, much more powerful than she can resolve on by herself. And okay, so this is really a very interesting observation. And I want to first, before I'll give some example of why this is true, I want to first say why Shor's algorithm can be viewed as a special example for this thing. Okay, so it's not exactly a special example, but if you look at the prover and you replace it by a quantum computer, which means it's not all powerful, but now it's more powerful than the verifier. The verifier is still a classical entity, but now the prover gets to be a quantum computer. So now, if the quantum computer interacts with a verifier and tries to prove to it that the factors of a number are really p and q, then it just sends it to the verifier, p and q, and the verifier only needs to multiply them and verifies them. So it's a special, very redundant example for the interactive proof, with the prover replaced by the quantum computer. Okay, so we'll get back to this. Of course, we would ask whether this picture can help us in testing a general quantum evolution. But before, let's understand why interaction helps. Okay, so this is a story of, suppose, this is a story that had nothing to do with quantum physics. Suppose I want to claim that I know how to count the number of leaves in a tree. So there are 9 billion leaves in this tree, I tell you. And of course, you don't believe me. I mean, why should you believe me? So here's a way where you can use interaction in order to be convinced. So you ask me how many leaves there is in a tree. I say 3 billion and 100. Okay, so then you ask me, turn around, and you make sure I'm not looking, and you pick a random number between, say, 1 to 10, and say you got 4, and you tear off 4 leaves of the tree. Okay, and then you ask me again to turn around, and you ask me again, what's the number of leaves in this tree? And if I tell you it's 3,096,000,000, then you say, okay, she knows maybe how to do something, but maybe she got lucky. So, or maybe she peaked. So you try again and again, and you make sure I'm not peaking, and if I succeed several times, then you probably get convinced that I know how to count leaves in the tree, even though you don't know how to count leaves in the tree. You can't verify the number. So this is how interaction and randomness can help you be convinced of things that are that you can't do on your own. Okay, so so it turns out that you can take this idea and make it work for testing quantum mechanical evolutions, again, using interaction and randomness. So the point here is really you replace the all-powerful prover by a quantum computer, and now you're treating your quantum system that you're trying to test as an adversary. Okay, so you want to think of it as the worst thing possible, that is trying to cheat you in the worst way possible. Now you're treating it as an adversary, and you're interacting with it. And it turns out that by these interactions with quantum provers, you can get convinced of whatever evolutions the quantum computer can perform, even though you cannot simulate it. There's a caveat that you need to actually hold a small number of quantum bits and trust those small number of quantum bits, but still you can, using the small number of quantum bits, you can get to trust a full, highly complex quantum evolution. And this is related to various interesting ideas. I just want to give you a very sort of the beginning of the argument of why it would work. So suppose I'm thinking of a much, much easier task, which is this. I have a quantum bit, and I want to send it to a quantum computer. I don't know the state of the quantum bit. I want the quantum computer to remember that state, to keep it nicely, and then I want to get it back without any change. But I don't know the quantum state that I'm sending. Okay, so how can I make sure that the state I've gotten is really the right state? So here's a way that you could do it. Suppose you have a two-dimensional Hilbert space. That's the state of a qubit. You can encode the state by some random code. So you take this two-dimensional manifold, and you map it randomly into some two-dimensional submanifold of a larger vector space. Say, for example, by this map of, just for the sake of this description, take psi and two more qubits at the state 0, 0 and apply some random unitary. So this maps this two-dimensional space into a random two-dimensional space. And now, when you get the state back, you can just test that the state really belongs to the random manifold that you put it in by applying the inverse unitary back and checking that those qubits are really in the state 0. Okay, so the prover cannot, the quantum computer or whoever you're interacting with cannot really manipulate the state, because in order to do that, he needs to stay in this manifold, but he doesn't know where the manifold is, so it will probably get out of it and it will be detected. Okay, so it's crucial that the manifold is random, meaning that you're using some random encoding. Okay. So an open question is, can a classical verifier be convinced by quantum mechanics? Is it possible, if I'm completely classical, to be convinced by the power of quantum mechanics? And a partial answer was given by Reichert, Unge, and Vazirani last year, where they showed that if we can assume that two quantum computers are entangled, then the answer is yes. Meaning, if the experimentalist or the verifier is interacting with two provers or two quantum computers which are assumed to have entanglement, and other than that they're separated, then one can use these basically the assumptions on the very strong correlations on EPR states that I talked about before, in order to really verify that what they have is the entanglement that they're trying to generate. And again, this is sort of a substrate of entanglement, and on top of that, you can perform any computation. Okay, so you can be convinced of a general quantum computation that takes polynomial time. We don't know whether this can be done just by a classical prover interacting with a quantum verifier. And it's a fundamental question whether classical systems can be convinced that something quantum is going on, or that quantum power, computational power, is performed, though they are completely classical. Okay, so the way this is done is essentially by viewing these two computers as two prisoners. That if you want to treat as they're trying to cheat you, well, best would be to separate them so that they cannot coordinate their stories. So this is how this buys you some power. Okay, so this is related to many, many very interesting questions that were part of the focus of the conference last week, which is, for example, certifiable randomness, where these games that you can play with EPR pairs and their measured output, you can actually certify that this measured output is random, is truly random. And it's also related to the question of device independence, where you have a question of how much you can rely on the security of cryptographic protocols if you don't know anything about how the devices were built or what you can say about them. So you want security that does not rely on this, and you can achieve that. So, okay, so there are many, many interesting branches here. I want to mention one thing which is more general than just quantum computation, which is, so this is, this point of view of an interactive experiment can actually be viewed as more generally, right? I mean, we often talk about experiments with systems that we don't really understand. And maybe they're too hard to simulate. And the question is it possible to sort of generalize this idea to other systems that might be very difficult to understand and use this more structured paradigm of interaction, inspired by interactive proofs, to get some leverage of when testing complicated physical systems or biological systems or what have you. Yonatan Yaari did his PhD in philosophy of science, developing a theory of interactive confirmation, and based on those things. And I don't know. I think it might be very interesting to find other applications of those more structured. So putting experiments in a more structured way into interactive experiments. Okay, so let me move on in the last 8 minutes of the talk to the second part, which is the robustness of those multiparticle entanglement states. Okay, so this is based on many, many things, and of course I'm not going to cover them all. But I do want to give you one small idea that's coming from there. So really, the starting point is very, very much related to the previous point, which is verification of claims. The notion of verification is something very profound in computer science. And perhaps the most important way to capture it is the class NP, non-deterministic polynomial. And, okay, you all, even if you don't know this, you know this because it's basically, so here's an example. It's basically the class of problems which, if you're given a solution, you know that it's really a solution. So most problems are like that, or many, many problems are like that. Thousands of problems are like that. So here's an example. You're given this graph, and you're given local constraints on this graph. Each node can have a spin pointing up or down, and the local constraints tell you if the spins like to point in the same direction or in opposite directions. And so red like to point in opposite directions, and green like to point in similar directions. And you're asked whether there is a configuration that satisfies all constraints. And here, I think there's no such configuration, but because this configuration violates one constraint. But obviously, if you're given such a configuration, you can, and you're asked whether this configuration really satisfies all constraints, you can test it. You can check it. But given a graph, it's very difficult, possibly very difficult, mainly if it's very, very big, to find such a configuration, even if it exists. Okay, so this is an example of the class of problems NP in which a solution, if given, can be verified efficiently, but it might be very hard to find a solution. Okay, so why should you care about this if you're a physicist or a chemist or someone who is not interested in computer science? So it turns out that the very basic problem in computer science, which is essentially a slight generalization of the problem I told you before, is simply a special case of the major problem in condensed matter physics. Okay, so let's go back to the problem that I mentioned before. So imagine now that you're given, instead of a graph, a slightly more general thing, which is a set of local constraints on Boolean variables, and each such bracket corresponds to such local constraints, say on 2 or 3 variables, and you want all of the constraints to be satisfied, or as many of the constraints as possible. So this is called a CSP formula, constraint satisfaction formula, and you're given such a thing, and you want to either minimize the number of violations, or to find the optimal assignment, or to find some approximation. You can think of various things. So this is a generalization of this thing. It's also a generalization of the notion of a mathematical proof. You're given a theorem, and you want to know if it's correct, or does there exist a proof of some limited size for this theorem. This problem, too, can be phrased in this way. So it turns out that this description is simply a special case of something which is at the heart of condensed matter physics, which is the notion of a local Hamiltonian. So here is the analog of the CSP problem. You're given a local Hamiltonian, which is a Hamiltonian acting, say, on n particles, n two-state particles. Each particle replaces a Boolean variable here. And it's a sum of local constraints, so a sum of local interactions. Each interaction involves only 2 or 3 or 4 of the particles. And what you want to do is you want to find the minimal energy state of this matrix, or a state which approximates it, or the minimal, not just the ground state, not just the ground energy, but also the ground state, or some approximations of it, etc. So this is simply a generalization of this, or this is a special case of this. And I won't say exactly how the proof goes, but you can sort of see the connection basically by replacing each constraint here by some energy terms, which gives an energy penalty if you violate this constraint. So if you take this and phrase it in this language, you get constraints which are commuting and in the computational basis. But the local Hamiltonian problem, which condensed matter physics is facing, is more general because the constraints need not commute and they need not be in the computational basis, in the usual basis, or in the same basis. Okay, so the thing is that when we allow this generalization, we enter again into this high complexity regime of quantum states, because the ground states can now be highly entangled. So we can ask all those questions about all those questions that computer scientists ask, but now about those questions from condensed matter physics with multiparticle entanglement involved. So what is the most interesting question that we can ask that comes from computer science? So, okay, I'll tell you now. Perhaps the most interesting result from theoretical computer science in the past 25 years, so that we can try to take it and map it to the quantum world. Okay, so if you haven't heard this is quite shocking. How many people here have heard about the PCP theorem? Okay, so for those of you who haven't heard, this is really unbelievable. But it's true. It was proven a long time ago.
That they didn't hear about it?
No. It's actually maybe. So what does the PCP theorem says? PCP for probabilistically checkable proofs. So what it says is this. Take your NP problem, and remember NP is a set of problems which can be verified efficiently. If you're given a solution, you can verify it, but finding the solution is difficult. Okay, so this is the verifier who is supposed, given a solution, here there's X which is missing, and Y is the suggested solution, and the verifier is supposed to be able to take the solution and verify that it really is a solution. So think of a theorem and a mathematical proof, and the verifier is supposed to verify the mathematical proof. So then the PCP theorem says that there is a way to translate this verifier to a new verifier, which takes a slightly longer input, a theorem which is translated to a slightly longer version, such that if you're given the proof, a proof for this theorem, it suffices to read only a constant number of bits from this proof to be convinced if the proof is correct or not. So if you're reviewing articles, this is really something that you need to remember from this talk. Except it's not practical yet. But it's not, I don't know if it's far. Is it far from practical?
There are actually people who are working on actual applications. So maybe in the near future.
Yeah, so that sounds like building a quantum computer answer. Okay, so we're working on. I mean, people are working on that. But in theory, these translations are efficient, and this is completely remarkable. That really there is a way to map mathematical theorems to such a format that the mathematical proofs of those theorems can be verified by just looking at a small number of places, which basically means that okay, let's first see the way it's written. So NP is equivalent to the class of languages in which the verifier reads only a constant number of bits from the proof, random. And there's a different way to phrase it, which is the set of problems that we were talking about before, the NP hard problems, like finding finding a configuration with energy smaller than some number for that graph. Well, this problem is equivalent to a problem which seems much, much easier, which is distinguish between whether the graph is completely satisfiable, or that is, you can satisfy all constraints, or you have to violate at least 10% of the constraints. So approximating the number of necessary violations to within 10% is as hard as finding the number of violations that you need to violate. So, okay, now how does the proof go? I'm not going to get into. It looks a bit like holograms. So it looks a bit like you're taking a proof with a problem in it, a small problem, and then you sort of spread it all over the place, and now wherever you look, there is a problem. If there was a problem in the beginning. If there wasn't any problem, nothing happens. So, okay, I think this is the most influential result in theoretical computer science over the past 25 years. There's many, many applications to it. And maybe from a physics perspective, I would like to say that whereas the issue of finding ground states is NP hard, this was known long, long ago by Aharonov, finding those optimal assignments to graphs that I showed you before. The PCP theorem says that even reaching the Gibbs distribution at room temperature is NP hard. So for a system to relax, there are systems such that for them to relax to their Gibbs distribution, they need to solve an extremely difficult problem. So it will take them exponentially long to relax to their Gibbs distribution. Now, they are complicated systems, but there are such systems. So this is what the PCP theorem says. It tells you how to construct such systems. Okay, and this is what I mean by robustness. This hardness is maintained also at room temperature. A different way to say it is that it's spread all over the place. So the problems are spread all over the place. Okay, a problem and a proof is spread all over the place. Okay, so as I said, I'm not going to give the proof of the PCP theorem. It's highly complex and quite long. But to the physicists and chemists in the audience, a possible way to think about it is something like a renormalization group approach, where you start from a small problem, and then you do some renormalization step and spread the problem a little bit to a slightly larger scale, and then you repeat. And this sort of makes the problem spread all over. And the only thing is that, well, in order to do that, you encode the problem into more bits, and you somehow make sure that they are encoded in a structure which can be tested locally. So that sort of, if it's not in the structure, you will find it everywhere, or easily. Okay, so this is sort of a picture of making the problem larger, and then you somehow have to reduce back to your original size of constraints. Okay, so you are not supposed to really understand this. This is just to give you some intuition. And then the question is there a quantum PCP theorem? And I'm not going to give you the exact the formulation of what a quantum PCP theorem looks like, but I think I've given enough introduction to give you an intuition of what that would be. And well, think of an attempt to smear a problem all over the place, but now you have to do it for states which are multi-entangled. So for states of many, many particles which are highly entangled, highly correlated all over the place. And unfortunately, we have no idea how to do it. There's just nothing of the classical techniques seem to work. And I want to end my talk with trying to give you some peek into why that is true, because it's a very fundamental thing that we encounter again and again when we handle multi-particle entangled state. Okay, so so the real issue is the notion of is the problem of the fact that multi-particle entanglement has a global versus local issue, meaning that states which are highly entangled could look locally the same, but globally could be completely different, because entanglement is something that is spread all over the place. And here's an example. Take the EPR pair that I've talked about before, slightly modified. Now it's instead of up, down, minus, down, up, it's up, up, minus, down, down. It has the same type of entanglement. And so this would be the, say, the minus state. So up, 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 minus, down, down, down. And then consider another state which is the same except a plus here. So these two states, is easy to see, they're orthogonal. But if you look at them locally, each qubit behaves like a completely random state. So locally they're the same, but globally they're orthogonal, they're completely different. And this is really the essence of the problem, because we are handling things locally, coming from classical intuition. Everything we do is local, but we cannot even distinguish between orthogonal states globally, between completely different states. So nothing seems to work. Now, really this boils down to understanding what types of entanglement we can encounter. And I'd like to point at, and this brings me to the topic of the third conference. So the PCP, the question of PCP would be an important part of the second conference. Okay, so, right? Is that? And this brings me to the topic of the third conference, which is you would like to understand better quantum states. So really, the question of quantum PCP can be made much, much simpler, and still we don't know the answer to it. What Hamiltonians have ground states with robust entanglement? So even if we don't care about the mapping between the original Hamiltonian and the final Hamiltonian, the translation between one format of the theorem to the next, the quantum theorem to the next, even if we forget about the mapping and just ask what kind of Hamiltonians can be the final Hamiltonians, what kind of Hamiltonians have robust entanglement in their ground states, we don't know how to construct such Hamiltonians. You might have heard of topological order, and this might look like a good candidate, but it's not. I'm happy to explain later why offline. But really, we can ask a much more general question. Can we classify entanglement, the structure of entanglement that are possible in ground states of Hamiltonians, in any useful way, and understand what kind of entanglements appear there, such that we can manipulate them in efficient ways, or in any way that we understand. So let me point now to the lecture on this topic, or related topics, that's going to happen in May, and that's the second open question on this open lecture on the Quantum Hamiltonian Complexity program. And thank you for your attention.
So I'm one of the newbies here who hasn't heard about PCP before, so maybe my question is a little bit naive, but it seems there are two aspects. The second one that you mentioned is that you say it is as hard to find this 10% approximation energy as the ground state. And in a way, intuitively I can feel that's probably okay, but it's certainly nothing to celebrate about. But then the other part was that you find a somewhat larger description of the problem, and that actually then helps you maybe at some time in the future finding a solution because you only have to sample, a finite number of bits. Can you elaborate how that might help, for instance, to find the solution to a traveling salesman problem?
No. The point is that you only say that a problem that seems easier is actually as hard as the traveling salesman problem. It's not that these are bad news. You were right in the beginning. Okay. These are not good news. I mean, they're good in the sense that we know better what is going on, but I wouldn't say that it.
To understand that these things are really hard.
Yes, they're even hard when you only try to approximate it like really crudely.
Can you say what you meant by robust entanglement?
Yes. So really Hastings posed a conjecture which said that there exists a family of local Hamiltonians such that not only the ground state of each Hamiltonian in the family is highly entangled, and by highly, I can tell you what highly entangled is later, but not only that, but also all low energy states, below energy, say 10% of, where m is the number of constraints, so m over 10, energy less than m over 10, are still all highly entangled.
What is
so,
the family direction?
I'm sorry?
Why is there a family in this discussion?
Because you need to, the size goes to infinity. Okay, and we don't know how to construct such Hamiltonians. So for example, in the toric code, it seems like there are topological order states which have their entanglement structure related to topology. They seem to be good candidates for robust entanglement because topology is robust and they're known to be robust in many, many different senses. But they're not robust in this sense because you can easily find not ground energy states, but low energy states, but by violating only the constraints along the red lines. And by violating only those, you can find easily ground states which are only locally entangled. Just find the ground state of this thing, and this thing, and this thing, etc., in tensor product. So they are not good candidates. And anything on a lattice will not be a good candidate because of this argument.
What simulations are you designing?
I'm sorry?
What computer simulations are you actually designing?
So maybe Ignacio is a better person to answer this question. Do you want?
Well, people are trying to build some experiments to simulate Haber models, so models that are interesting type of point of view to see how electrons move in solids and things like that.
Yeah.
This is kind of trivial, but when people say that we don't understand quantum mechanics, I mean, they're saying that we don't really understand how to write down measurements in like a fully quantum system, right? So you're not saying that we actually understand that. Right?
No, I said only for this talk. I'm saying that it's kind of this is sort of a spoiled approach to saying I'm not understanding. There are different levels of not understanding. This regime we really don't understand because we have no idea how to work with it and make predictions. In the sense of in the measurement problem, we don't understand it, but we can make all predictions. So I find it different conceptually. Yeah.
So earlier in the talk, you had this slide in which you proposed that this high entanglement regime is sort of a different limit in which we think about physics. And all the other limits you listed, some things become simpler in physics. Is there any expectation that some things become simpler here?
I think this is an excellent question. I don't know. I mean, to the best of our knowledge, I don't see how it becomes simpler, but maybe from a different point of view, it might become simpler. I don't know.
Any more questions? Well, we thank Dorit. The program continues the entire semester, and Dorit and many other experts on quantum computing are around, and you're welcome to come to the Calvin Lab and discuss it. Okay, thanks very much for inspiring.